the actual reason that I sent in proposal for this talk was because I've seen that people are discussing concurrency, and they're talking about actor models, and they're sort of taking a very theoretical approach to this concurrency. So I thought I would just explain a little bit about the true and a bit more sort of the practical side of it. Well, in the 1970s, the sort of job I was doing at Ericsson was writing assemblers for small, simple processors. And that would be processors to control something, and they would not have any operating system or anything. They would have like a few thousand words, and that was all. And people were writing control programs for that sort of thing. And such a program system would look like this. There would be program, program, program. And what the executive system would be actually a little what's called job control monitor. It was actually would call one program after each other and then go run and call them. And there would be only one entry point to each program. So the first thing the program would have to do is to sort of check its state. What was I doing now? And then sort of jump to the appropriate sequences. So it was a rather simple type of programming, and each program must ensure not to spend too much time, because then it was just taking time from the other programs. Because, I mean, this was not a scheduler, it was a job control monitor. Then sometime I was involved in creating this PL163. There was a new processor in Ericsson, which had the number 163, and we were supposed to develop an assembler for that. We created a PL language. And I don't know if you've heard of PL360, invented by Niklaus Wirth. It looks like a high-level language with if, case statements, etc. But actually it was working down on register level. It would contain statements like if register 5 equals to 100 then, etc. And so it was actually on a very low practical level, but you got very quite understandable, nice programs, better than ordinary assembler. And then we hit on the idea of developing a simple type of scheduler that was so that when the process was running and it came to a wait statement, it was waiting for some message, then this scheduler would sort of remember, aha, there it was. And then when this message arrived, it would then continue from the wait statement down further on. I mean, you don't think this is very, very advanced, but then it was quite a new idea, and this is actually when Mike and I met, because Mike was a user of this computer and this language, and I was involved in inventing it. And we invented some sort of buffers to send messages. The idea is that if there were too many messages, they would be queued, and if there were too many processes waiting for the messages, they would be queued instead. And actually, it's since then Mike and I have teamed up and continued working. So this was a little bit more advanced than the assembler, and a little bit more advanced than the job table monitor. But then the big guys moved into this. I should say, one person who we owe a lot to, that is this person, Niklaus Wirth. He created Pascal, you know, the data types, integers, reals, records, sets, etc. And then he created the language called Modula, which has modules, processes, process communication. He had also invented PL-type languages. PL360 was used to develop a Pascal compiler on the IBM machines. So actually this is a person we owe a lot to. This is Modula, and then Modula 2. That was invented by Niklaus Wirth. He was professor in Zurich. And the difference between this language and Pascal was that it would be modules, which are sort of design units, and there would be processes, which are the sort of dynamic units when you execute, and then there's process communication. Well, the process communication was actually through something called an interface module. So the whole idea is that if two processes were sort of talking to each other, they would do it through this interface module, and only one of them could be executing at a time, so that they wouldn't sort of confuse things for each other. Then, now this is when the big guys moved in. I mean, CCITT, that's a great big international organization in Geneva that standardizes on the GSM. I mean, the reason that telecommunication systems can sort of talk to each other all over the world is due to all the types of standards created by this organization. So then they thought, yes, let's create a standard programming language so that we would have different suppliers writing programs, and we could all understand each other's programs because we sort of recognized them, etc. And it was actually based, it's in a Pascal tradition. There were modules and there were processes, and then there was process communication. Well, this is the interesting thing. I think that regions came from Philips, buffers from ITT, and signals from Ericsson. The thing is that there was also a system description language, which was a language mostly for flow charts showing state machines talking to each other through signals. This is, I urge you, read this through carefully. I mean, this was state of the art in the 1970s. They didn't quite know. I mean, how do we do process communication? So they couldn't quite agree. So this is a result of a committee. So they put everything in. The problem is that you can't really combine those techniques in one system. So actually in 1999, CCITT stopped maintaining the chill standard. It wasn't really a success, and this is one of the reasons. Then another big guy moved in to this area too, and that was, this is United States Department of Defense. They decided that they wanted a standard language they could prescribe in all contracts that people would write the programs in their prescribed language. And this was a major industry. I mean, I think they got about 8 proposals, which were cut down to 4 proposals, which were given color codes, and they were sent out all over the world. People could comment on them, etc. And then in the end, it was a green language that won. And you can see that it's in a Pascal tradition. But they had to do something by themselves. So instead of modules, they called it packages, but it was essentially the same thing. And instead of processes, they were called tasks. But they made it even worse, because like in a procedure, you could have packages, and inside a function, you could sort of split into different tasks, etc. So it would be completely cyclic. The end effect of this was that it was rather tricky to design a compiler, and it was very tricky to use it as well. And then they invented task communication through something they called rendezvous. This means like this. You have, well, this is 2 processes, but they call them tasks, and this would then call like a procedure in this task. Here would be a so-called entry point. So it would make call, procedure call, and then get the result back. And this would be also a synchronizing point, so that if this was not quite ready, this would be waiting, or vice versa. So it would be communication and synchronization. Well, the problem with this, it made for very rigid systems that were sort of stuck together. And the whole thing then is, that is what they wanted, because they thought that now with type checking and all that, we would be able to assure that this is a correct system. It was just that it was rather awkward to use. If you just want to send a message, you would have to have a buffer task. So first, this task does a rendezvous to send the information, and then this task makes a rendezvous to retrieve the information. So I think in actual fact, when Ada was used, most suppliers would invent some sort of shortcut by themselves. So, I mean, and then it took too long time for them to produce a reasonable compiler, and then actually C appeared and took over. So I mean, why did they make this so complicated? I mean, you are talking about sending signals or messages. I mean, why a rendezvous? Why is this? Well, the thing is simply that the people behind this, they were computer scientists used to writing sequential programs. Sequential programs will start, reads input, performs computation, and prints output. But oh dear, this is supposed to talk to this program. Oh, how do we do that? And then you saw the result, or else perhaps they would have a common sort of data area. So both this and this program would be able to look at, but then you would have sort of semaphores to say whether it's free or not to use, etc. Suppose your application is concurrent. If you start from a sort of concurrent background, life is completely different. And that was, of course, in the telecoms industry. You know that, I mean, if you lift the receiver, you press buttons, your telephone sends messages to the telephone exchange, etc. So they created a whole very complicated problem for themselves unnecessarily, just because of their background. But anyhow, we tried to make the best of it. So this was something we did in Ericsson also. So this, I mean, if PL163 was the first language we were involved with, the next one was Pascal. And that was because we could get hold of a Pascal compiler from University of San Diego, which was very popular then, and rewrote it or changed it so that it would handle modules process, but only process communication using signals. So actually it was almost like a subset of chill, but only with the signals. And this, like the PL163, they were used for various projects. But we were sort of mucking around with language design, and I have this photograph is hanging on my wall at home. It's all, I think, some 43 years old. This is me visiting Niklaus Wirth, discussing Pascal for telecom, a language we call Pastel. I don't really remember. The only thing I remember about was the name, and we thought that we would have very colorful manuals for it. But the thing is just that exactly when this visit happened, Niklaus Wirth was presenting Modula to the world. So I went to a lecture in Hochdeutsch where he presented Modula, and all the students, instead of sort of clapping like this, they were saying, that's apparently how Swiss students applaud. So that was very interesting. But then we had started working with Lisp and Prolog, and I wrote some interpreter in using Lisp, where there was some projects with 6 or 7 people involved doing the same thing in Pascal, and I overtook them in 2 months single-handedly. And that wasn't because I was so clever, it was just simply that Lisp was a very good technology for the job. And I mean, Mike Williams, he's standing down there, he's around in this area still. And Göran Båge usually comes to these conferences. He is also in the Erlang business. But you don't, who is this Evert Torstendal? Well, he was a person who changed the San Diego compiler to implement Pascal. And what we did, we went to the technical director of Ericsson and said, look, you've got plastics laboratories, soldering laboratories. I think you should have a programming laboratory. We could do it. And I think at that time, Ericsson was very successful with the AXE system and had lots of money, so we were given the go-ahead. And I don't know how often a few technicians can go to like the technical director of Ford or other huge companies and say, look, we would like to set up a lab. But we were actually allowed to start. And this is what we promised to deliver. And this is, well, here is our job description written in 1984. We promised to create a software technology for future telecom. I don't know today how we could be so self-confident. And then new technology. We were, but I think, the first to use Unix workstations. We're doing expert system graphics, other peculiar things too. Then, suppose you want a laboratory to experiment with telecoms programming. Well, you have to have a programmable telephone exchange. And this is what we created. This is a telephone exchange, and this is a VAX computer. You think this is very peculiar, but it isn't really. These are the telephone lines, and this is a tone sender, and this is a tone receiver, etc. And that means, and this is a switch, so that to send a tone, you would have actually to connect to the line to the tone sender and start it. And normally, this whole thing would be controlled by its own computer or processor. Well, the thing is that at that time, programming was much more awkward and not so much online like it's today. That is, usually you would write a program and then compile it on a VAX or IBM machine, and then you would get a tape, and then you would get to the lab where they had a telephone exchange, you would load it there and run it, and if you found errors or bugs, you would have to sort of go back to it. But here, this was what Per Hedlund did. He rewrote, changed this program so that all control messages were sent over to the VAX. So the VAX became actually the control processor. And now we could start doing fun things. And that's exactly what we did. I think we were about 5 people at least who started programming this, which in all sort of languages. We got hold of some Ada, concurrent Euclid, which was what, like Chill. This was a parallel functional language. That was actually like a parallel ML. Problem is that there was no sort, I mean, you had to start all the processes from the beginning. You only had static processes, which was a bit constraining. Some logic programming languages was something. The fun thing with this, I remember, is that Prolog has backtracking. So that had sort of fun effects. You can stop the backtracking by putting in cut. well, lots of cuts in our system. But before, you would make a call, there was an A subscriber and a B subscriber, blah, 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 talking to each other. And then when the A subscriber hung up, then the backtracking sounded, blah, 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 thought that the B subscriber was actually like an A subscriber, and he got a sort of dialing tone and could start a call. And I did the rule-based system, which was quite fun. I think in 15 rules we could sort of write the whole thing. But there happens also things. Rules would trigger quicker than we thought, so that if you pressed button 1, it would ring at the extension 11 because the rule for first digit and the rule for second digit both triggered, and etc. But this was reasonably scientific stuff. But then, this is a conclusion, and these are Mike's words. I recommend you read this carefully through. I'll give you a minute. You see, the thing is that we didn't reach the conclusion. This is a way how to do it. We learned a lot, but we didn't reach this conclusion. It was like back to the drawing board. And now Joe and Robert also joined. Plus, we suddenly got a serious user group who were going to do experimentation in telecom systems architecture, and they needed some technology for doing their prototyping. So now it wasn't just us in the lab sort of working all on our own. And, well, we didn't intend to invent a language. We thought perhaps they are done by international committees, but that's what happened. Really what happened was that it was perhaps a language. It was a virtual machine that was needed. I mean, if you need support for concurrence, etc., the language is like the syntax of the virtual machine. And then, well, would it be another Pascal? It wasn't EriML or Lisp or Prolog. It was something new. So would it be EriLang? And then I mean, anyone who studied a little bit about telecommunications know that there's a unit called ERlang. One ERlang. I mean, there's like Pascal or meter or Fahrenheit, etc. It's a physical unit. And there's something called ERlang loss formula, etc. So that's, oh yes, everybody knows the word ERlang. And because it's easier to pronounce than saying EriLang. And then we, of course, knew that there's a man behind it, a dead mathematician like Ada Occam Pascal. And then it had, well, the background like Pascal. But so it got the name ERlang comes from this unit in telecoms. And then you can follow, you can see here we presented all the results for these experimentations. And then Joe and Robert, we started the second round here, phoning philosophers' problems, using problems. Thing is that Mike and Joe were a kind of dream team. Mike knew everything about these languages and telecom, and Joe loved problem solving. So here is where we exploded ERlang to the world. Huge symposium, 2,000 people feeling the whole globe, etc. And there was one demo day when I think 8 groups of people were bussed around Stockholm, and they passed through our lab, and we gave a demo of this new language, ERlang. Well, who has seen ERlang the movie? Actually, that was our demo for this International Switching Symposium. So Joe thought that, oh, look, we made this demo, let's videotape it. I mean, we got it set up. And now you see there are different types of papers, implementing a functional language, use of Prolog for developing a new programming language. The first implementations of EriLang were in Prolog. Not very fast, but they worked. And then you get, here is International Switching Symposium in Yokohama. They were presenting prototyping using EriLang. And this was very interesting. There were 4 papers Ericsson presented at that conference. 3 of them were actually prototypes using EriLang. And now here is where Bogdan Hausman came from 6. Turbo EriLang, efficient implementation. It wasn't now it wasn't just prototyping for fun. No. Now it was getting for real. And here's a book. And the thing is that if we had created something like before, I mean, Ericsson Pascal manual was an Ericsson document, internal document. The EriLang manual was a book printed by Prentice Hall, and that was Joe's idea. And here, 3 wise guys, Joe, Robert, Mike, and we were at Belcourt, Morristown in December 1989, because they were people there interested in new technologies, and they have heard of it. And we spent a week there giving a course and so on. Thank you very much.
We can use the break to ask questions.